Hello everybody, this is video number 6 for MECH215 and today's topic is about weld structure. So we mainly focus on two types of welds, the butt welding and the fillet welds. So butt weld is basically have two plates end to end put together and you use a weld to connect them together. So this is the case most simple for analysis. So you basically have two different kind of loading conditions. You have a normal stress and you have a shear stress on the welds, and they both use the same equation. The second weld type is the fillet weld. So fillet weld is much more complicated. It has 4 different kind of loading conditions we have to look through. But in summary, you basically consider the weld's throat length and multiply with the length of the weld, so it goes that way. So it's the throat multiplied with the length of the weld. That's the cross-section area you used for the calculation of the stress. From the force, you divide by that area, you get your stress. For all the fillet welds, that's the case. So firstly, simplest case is tensile stress on the butt joints. So this is the figure. You have the two force pulling these welds apart. So the cross-section area are under the normal stress. And normal stress is equal to the force over the cross-section area. So basically consider this welds basically the plate. The cross-section area is H multiplied with L. For the butt weld under the shear stress, so the force direction actually goes this way along the weld, so the weld's cross-section is under a shear force. You have the same formula for the shear stress. You have the force over the cross-section area. So these two cases are very simple, and there's no difference compared to just look at the normal plate. For the fillet weld, the first case is you have transverse welds under the kind of tension over here. So you have this is the weld, it's under a certain tension, so this F is going to try to pull this apart. So we use the force over the cross-section area is our stress, and we always use shear stress. We ignore the normal stress, although in this case it's kind of over any point you have a normal stress and a shear stress. You have two components, but we inflated the shear stress to be like 1.414 times of the shear stress we got, and we ignore the normal stress. So all the stress components goes to that shear stress component. So the simple calculation is use the force multiplies the cross-section area with 0.707 H, that's the throat size, multiplies the length of the welds. So just always use this for the fillets. And this will include both normal and shear stress, but we represent with shear, no matter what kind of the stress it is. The second case is, so this weld is under kind of a two shear force. The force is along the direction of the welds. So the welds is this way, the force is going along, so trying to apply shear stress. And the shear stress is equal to the force over the cross-section area. So basically it's exactly the same formula. If you look at this, that's exactly the same formula. Okay, so these two are simple, just stress on the welds. Then case 3 is when the weld joint is in torsion. So you have a moment over there. So if you start from a force, apply at the end of the weld, and this weld symbol, it's two triangles, means you have one weld at the bottom, one at the top on the other side. So this is this one on this arrow side, and this is on the other side. You have two welds over there. This force will generate a reaction force and also a torsion moment. From this reaction force, you have the primary shear force. from this moment, you get secondary shear stress. The primary shear stress is the force F over the cross-section area. So this area, weld area, plus this area is your A. The secondary shear stress is M R over J. M is this moment. R is the distance of the point of interest to the centroid of the weld group. So this one you have 1, 2 rectangle. So it's symmetric. So the centroid is right in the middle. And this distance is the R. So you can see the large stresses happen at these kind of 4 corner locations. And divided by J. So this is kind of the tricky or difficult part. J is the polar moment of inertia. So you can see the whole thing is going to rotate around this in this plane. So the rotating axis kind of goes inside or outside of this screen. Again, so to do the calculation, the challenge bit is to calculate the J, so particularly the J. Luckily, we have a few standardized geometry. We can look up the table 9.1 for this torsion application. However, in a general case, these a few slides is explain a general case. You have 2 weld bead. Say this is T1D and this one is T2B. 2 different size weld bead, and this one have the G1 right in the middle and G2 right in the middle. So the total center of gravity is somewhere in between. So we have to calculate a lot of things, a lot of steps until we get this J. Until we got this J. This J. Okay. So J is this JG1 around its own centroid, then JG2 around its own centroid, then this first area around that new center of gravity, and this second area around this new center of gravity. So if we look at that, it has 4 components. This is first component, this area around its own center. This is this area around that point. So R is the distance here from this centroid G1 to the centroid of the overall structure, which is G. Then this is for the second G2 part. Okay, so with those 4 components, the JG1 is the moment of polar moment of inertia of this area around its centroid. And this polar moment of area is equal to Ix over Iy. And Ix or Iy, one of this is used for the bending, but this is a torsion, so you have to add these two together. So you look at, say, this particular area. Ix is T1 d third power over 12. So these equations, formulas are on the exam formula table. So when you are working on these kind of question, tutorial question, do the review, make sure that's the only document you rely on. All the formulas, information you need to have needs coming from there. If it's not in there, then you have to memorize it. So make sure you do that. Otherwise, if you refer to the book to do the thing, and then once the exam comes, you don't know where all these tables are because they are stapled together with like 30-page document. So make sure you use that formula table while you're doing the review. Ix, so x-axis is this one. So Ix is rotation around x-axis. So it's T1 d power of 3. So T1 d power of 3. So this d is kind of rotating around x, so that's get third power divided by 12. Iy is also look at this around the y-axis. So it's d T13. D T13. So actual JG1, this is only for this part here. You get 1 is around x, 1 is around y, adding that together. and for G2 it's the same thing. Well, T1 becomes T2 and then the D becomes V. Okay, so a good thing about this is you can see this T is much smaller than the D. D is the length of the word, T is width, so that's normally quite small. Then you have third power of this very small number compared to third power of the bigger number, so this part normally is only a fraction of this part, so you can ignore that part. And then you look at this G1 is actually proportional to the size of word. Okay, it's linear proportion to that. So we come up with a better solution over here. So we, instead of manually calculate each one of these J, we have a table with all this JU in the table. This JU is in the table, and JU is the value when the word size H is equal to 1. So if you find some words is in the table, make sure this words, for example, this is you have left and right, these two must be the same size in this case. If they are different size, like in the example, you can't really use the table, you have to derive it by yourself. So from here, you can calculate the centroid, so the basic centroid is in the middle. Then you can calculate the JU. This is when you consider H is equal to 1. For the actual J, you use this 9.6, and then you can use those 9.4 and 9.5 to do the calculation, find the tau. So the table goes on with 6 cases in total. If in the case you can't find anything from the tables, for example, this is a case it's not existing in the table, then you have to derive like this. You find where the centroid is, where the distance are, then do it completely manually. Okay? And also you have to look at this one, where it's in banding, you have to get tau 1 is V over A, tau 2 is MC over I. So here I is again another thing. You have a table to look at, but if it's not in the table, you then have to derive it by yourself. So it can be a very, very tedious question if we ask the question slightly different. So okay, this is the last case, fifth words loading with in banding. So in this case, the component is wired together at the end to fix on some fixture. The force is pushing at the other end. So this force will generate first primary shear due to the shear force, and then secondary shear. This is basically the bending normal stress, but we still use the shear stress value. Like we said, that's when we do the welding, we always do the shear stress value. And this tau prime, sorry, it goes downwards, and this tau double prime goes left and right, depends on where you look at. So on the top it's going to be tension, on the bottom will be compression. So to add these two together, basically because these two stress is perpendicular to each other, so you can just do the Pythagorean theory to add them together. Then you have table 9.2. This is a table for the bending properties, and you have a few standard geometries. One thing I want you to look is this case 2 and 3. So case 2 and 3. So basically it looks the same kind of geometry. The difference is this one have the weld beads on the left and right. This is only the weld beads on the top and bottom, and this direction is depending on the way we're bending it. So you can look at this words. In this case, you have top and bottom. Is you're gonna use this case 3. But if you, for the same kind of geometry, if you push this way, so this force pushing this way, you don't change this weld bead, pushing that way, then you have to look at this case B. Okay, so it depends on a lot of factors. You have to choose the suitable ones from the table. Just be careful. 2 and 3 can be confusing. Sometimes you're going to use the wrong one. Case 4, it's a U shape again. Then you have the upside down U shape. Then you have the rectangle. and this is T joints. So you have a little bit more cases than the other one, and you have circular in the end. So again, this IU is when you consider H is equal to unity, or the word size unity, not H, but the T is equal to unity, and that's what you got for the second moment of area. If you have to get the actual one, then you multiply with 0.707h to this IU, you will get the second moment of area for your particular question. Okay, so lastly, let's have a look at example. So this is example in the tutorial question, and I also promised to explain this this complete question in a little bit more detail. So firstly, let's look at the figure. So you have something fixed on a fixture. There's attachment on the fixture, and there's a force pushing down 25 kilonewtons. And we have to look at what happened to the weld metal, okay? So the throat of the weld metal. So we have the symbol over here. So this is a 9mm welds. Because you see the two triangle means there's a one weld on the left side and there's one weld on the other side. And by look at all these dimensions, we can get this weld size H is 9, and our T is 0.707 multiplied with 9. That's what we use. And D is the length of the weld. So this is a 200. So because this is 200 with 25 offset, and this bar is 15 offset, so basically this 200 is this one. And B is the distance between the words, so because this thickness of this bar is 25, so you have B is 25. But don't look at B, D, H, because sometimes they can swap the symbol. Just look at these dimensions. So the length of the words is 200, and the distance between the words is 25. And this is finding maximum shear stress. So first you have to look at, this is bending or torsion. In this case, because you see the words is word in the end of the thing, and you're pushing down, so it's kind of a bending condition. It's not torsion. Torsion is when you have words in the same plane on the word on the side. And we look at table. Which case is this? So you have words on the left and right straight down, and you have force pushing down, so you have this case too. Okay, the words on the side, you are kind of bending this way, and we can get from here, you got the IU, the centroid is right in the middle because it's symmetric, and the area, so we need all this to do the calculation. So we pick all that. So the first step is we identify what case is this. So it's case 2 in the table 9.12. Then we use this, putting those HDB in there, we calculate the IU from there. And the actual I is 0.707 H with IU. Okay, so that's, we got I. Then tau 1 is equal to F over A, the force over the cross-section area. You got 9.82 megapascal. And the moment, bending moment, can see original question, it's this 25 multiplied with 150. 25 kilonewton multiplied with 150 millimeter. Oh, sorry, I pressed the wrong button. So it's this one. It's 25 multiplied with 150. So that's our bending moment. And this tau double prime is MC over I. We have to look at the critical points. Is at the top and the bottom. You have the bending moment over the top or the bottom. That's the same value. So the distance C is half of this size. Right? The center is there. So C is half of the size. So what you got is you have your, this is the bending moment. Okay, multiply with distance. D is 200, so you multiply 100, and I is this. You have to multiply with 10 1000 because this calculation here, just see F is actually in kilonewton, moment is in Newton per meter, and C is in millimeter. So you just have to sort out the unit in here, and I is equal to millimeter force power. So make sure this unit is kind of aligned to each other. So you get 44.2 megapascal, and this is sigma 1, sigma prime, sigma double prime, and total sigma is adding those two together. That's the total stress. So that's it for this video. Thank you for watching this. If you have further questions, I'll try to close it.